When we started Chapter 4, we mentioned that there were four basic ways to connect circuits. In 4.3 here, we're going to be looking at parallel circuits, which is the second major method. Parallel components and circuits are another fundamental way to connect electrical and electronic devices. A parallel circuit is characterized by having the same voltage across every component in the circuit. And you'll notice here we have a voltage source, and that source is connected directly across every component. Two components are connected in parallel if both ends of each component are directly connected together. So if we were just looking at R1 and R2, we know they're in parallel because both ends of said components, they're both connected to each other, and hence these two are in parallel. Likewise, if every component in a circuit is directly connected across every other component in the circuit, then the entire circuit is in parallel. And you can see that every single component here is directly connected across each other, so we can say that this entire circuit is in parallel, and every component in a parallel circuit will have the same voltage across it, and that would be our applied voltage. Okay, the following principles apply to parallel circuits. All components will have the same voltage across them. The total current is greater than any one branch current. And we will see that as we look at our circuit calculations. We'll find that the total current will be the sum of all three component currents added together. The total resistance is less than any one branch resistance. And what we'll find, there's a rule of thumb concerning parallel circuits, that if we have multiple resistances in a parallel circuit, you will find that the total resistance will be less than the very smallest resistance. So total resistance is less than any one branch resistance. Total power is greater than any one component dissipation. So the total power is going to be the sum of all of the component power dissipations added together, and that will be greater than any one single component dissipation. And then we have some formulas, mathematical relationships. In parallel circuits, Kirchhoff's current law is used to analyze the circuit, much as Kirchhoff's voltage law was used in series circuit. And so here we have the formula for parallel resistance. We'll be applying this in just a couple moments. And then here we have the current relationship. The current will be I1 plus I2 plus I3, etc. The voltage, the applied voltage, will be the same across V1, V2, and on and on. The power dissipation will be the sum of the power dropped across all components. Okay, first of all, let's look at our formula here for resistance, for parallel resistance. When we talk about the parallel resistance, what we're talking about is here we have this voltage, and it is connected across two components. Now this could be many components. Just for simplicity, we're just going to deal with two to start with. But what we're calculating is what is the total resistance that this power supply sees. It sees 1K in parallel with 2K, but what is that total resistance? And this is the formula to calculate that. So let's, why don't we just write out the actual values here, and then we'll do a little bit of calculating. So first of all, we'll start out with 1 over, and the first one is 1 over R1. Now R1 in this case is 1K, so that would be 1 divided by 1,000. And then we're going to add that to the sum of 1 divided by, and the second component here is 2K, 2,000. And we're going to add those up, and then we're going to do 1 over whatever that value is. Now 1 over 1,000, just let's see, that's going to be about 1,000th, or 0.001. And 1 over 2,000 is going to be half of that, so that would be about 0.0005. And so roughly, if we added these two together, we would get about, let's see, 0.0015, I believe, about 15 thousandths. And then so our calculation would look something like this: 1 over this value, and that would equal our resistance. Now, I don't expect you to do this kind of thing in your head, so let's pull up a calculator, and we'll look at a little bit how we would do this. So first of all, we want to know 1 over R1, this value right here. So let's say we'll click in 1,000, and then we have a function of 1 over x. And so if we click on that, we will see there we have the 1,000. That's 1 exponent minus 3, and that is equivalent to this value right here. And then we're going to be adding it, so let's go plus, and we'll say 2,000, and we'll do the same thing, 1 over x, and then let's look at our equal sign and see what the total is, and that's 1.5 thousandths, and so that is this value right here. Now remember, our total resistance is going to be 1 over this value, and so again we would do our 1 over x function, and here we get our value of 666.66 ohms. And so if we were to redraw our circuit here, if we said here's our little power supply, and if we put the resistance over here, we could, the equivalent resistance is 666.66 ohms, and then our applied voltage is 10 volts. And so that gives us our parallel resistance. Now that is, remember, 10 volts, when it's applied to these two components, that is the resistance that is felt. That is the parallel resistance. Now something, your book doesn't go into this, and my real concern is that you be able to use this formula. But just as a point of reference, let's take a brief look at what is it we're actually looking at. Do you remember in earlier chapters we talked about something called a Siemens, and we said that a Siemens was the reciprocal of resistance. It was 1 over resistance. And what we're actually doing here when we said 1 over 1,000 plus 1 over 2,000 is we were actually adding up the total Siemens. And when we got this value right here, this was actually the total Siemens. And if you remember that resistance equals 1 over the Siemens. And so we did this so that we could calculate the parallel resistance. So we did 1 over S, and that's what gave us this value. So essentially when you calculate parallel resistance, what you're doing is you're adding up the total conductance and then taking the reciprocal of that total conductance and getting the resistance. Now, your book doesn't go into this. I'm not going to make an issue of this, but I just wanted to give a little background on why this particular circuit actually works. If you don't want to know why it works, that's okay, but just be able to use this formula to calculate parallel resistance. And remember, the thing that we mentioned either in the intuitive relationships was that the parallel resistance will always be smaller than the smallest value of resistance. So in this case, remember that R1 is the smallest value, 1K, and the parallel resistance was smaller than the smallest value of 1K. Okay, let's go on and do a few more calculations here. We calculated the total resistance. Why don't we throw that in here again, and I'll quickly draw this in. and we said our total resistance was 666.66 ohms, and our applied voltage, again 10 volts, that's the equivalent resistance. Okay, now, so for the current, remember current equals voltage divided by resistance, and so here we have an applied voltage across this component, so we have 10 volts divided by 1 k ohm, and I already did this right here, so that is going to be 10 milliamps. Remember, we have the same 10 volts across R2, the 2K here, so that would be 10 volts across 2K. That would be 5 milliamps. So our total current across both components is going to be 15 milliamps. And the another way to have done that would have been to, this would have involved the calculator, but remember we calculated the total resistance. So we could have said 10 volts divided by, what happened here, just a minute, 10 volts divided by 666 ohms should yield 15 milliamps as well. And if we were to grab our calculator real quick, let's see if we can quickly confirm that. If we take 10 divided by 666.6 equals, and 15 milliamps is in fact the answer. Okay, so we calculated the current. Now the voltage VA, well, it's kind of obvious here. The applied voltage is VA across R1, R2. It's the same thing, so there's nothing profound about voltage. Okay, power. We're going to be looking at the total power is going to be the sum of P1 plus P2 plus however many more components you have. Now again, we could, in fact, well, let's look at the individuals first. So the individual voltage drop across the 1K was 10 milliamps, and this is going to be the power here. So 10 milliamps times the 10 volts would give us, what, 100 milliwatts. That would be across R1. So remember, 10 milliamp, that's the current through this component times the voltage, would give us that current. Then across R2, the current was 5 milliamps times, again, the applied voltage, 10 volts equals half of that, 50 milliwatts. So we should have 150 milliwatts of power. Now, we could have done this another way. We could have said our total applied voltage times our total current. So in this case, we could have said 10 volts is our applied total voltage times the total current, which was 15 milliamps, and it's not rocket science. 10 times 15 is going to be 150 milliwatts. Okay, so those are our basic calculations addressing resistance, voltage, current, and power for basic parallel circuits. Now, parallel voltage sources. Sometimes more power is needed in a circuit than can be supplied by a single voltage source. And so what we're looking at here is, let's pretend we have a voltage source and we have some parallel components connected to it, and let's say that we've got a bunch of them. And so what we're going to find here is that the current draw across all these components is going to be quite significant, and that this power supply on its own may have difficulty providing that much current. So what you can do is you could put another power supply in here, and connect it in parallel with this power supply, and this could help in supplying the additional current needs of all these components. Now, if you're going to do this, it must have the same voltage. So if this is in common batteries, this is a 1.5 volts is a common side. Let's say we have another 1.5 volt source here. This will not be a problem. The source voltage will continue to be 1.5 volts. It's just that you'll have additional current to supply the needs of all of these components. Total voltage will be the same, but the current capacity will increase. Okay, in this lesson we looked at some of the calculations concerning parallel circuits. We calculated resistance, voltage, current, and power. And we looked at, well, what is a pair? We looked at intuitive relationships in parallel circuits, and we defined parallel circuits.